Now, then melting. Melting, there are two curves. One is for the left one is for the substances that expand on freezing. Okay, that is the case of water. Okay, and the right one melting curve, or this is also called the fusion curve, is for the substance that contract on freezing. This is the nature for most of the pure substances apart from water. And then we have the vaporization curve, okay, and which ends or terminates at the critical point. What is critical point? We have already discussed in our earlier lectures. So if you look into some of the solid liquid vapor triple points, the data of the different substances, you'll find that for hydrogen, it is minus 259 degrees centigrade and the corresponding pressure is 7.194. Similarly, oxygen, it's very low pressure. These are the pressures below the atmospheric pressure lines. Whereas if you go to the carbon dioxide, you'll find its triple point pressure is much higher, 520.8 kPa. For water, it is 0.6113. Now, what is the specialty then for the carbon dioxide? If you look into that, let me dictate the point. Passing from solid phase directly into the vapor phase is called sublimation. We have already discussed. For substances that have a triple point pressure above the atmospheric pressure, for example, carbon dioxide. Okay, sublimation is the only way to change from the solid state to the vapor phase at atmospheric conditions, because they are already in this zone below the triple point operations. Okay, so any doubt about this point, about the PT diagram? Please respond.
No, sir.
Now, this is basically the PT diagram for carbon dioxide. The y-axis is the log axis for corresponding to the pressure, and the x-axis is the temperature. You can see the pressure is much higher than the atmospheric pressure conditions. So, if you look into the PT diagram for the different substances, a pure substance can exist in number of different solid phases. Okay, so what the phase transformation diagram shows? It basically shows is how the phase transformation process in the PT diagram will look as the substance goes from one state to the another state. So what are the phase changes we have seen? We have seen from solid to liquid, then liquid to vapor. We have also seen during sublimations from solid to vapor. But there are substances, okay, there are situations where a solid state change from one state to another solid state. Those kind of changes are called allotropic transformations. Okay, in those transformations also, a substance may appear in different phases. For example, let me show you. This is the phase diagram of the water. So this is the triple point. Okay, here you can see the solid, liquid, and vapor are in equilibrium. If you go below the triple point, there are solid and vapor in equilibrium. If you go above the triple point, and if you are in this region, in the temperature region higher than the triple point, so you will see that it is substances are basically liquid. Then it will go to the liquid to vapor equilibrium. Now there are different kind of solid states of the ice. Ice 2 state, 3 state, 4 state, okay, 5 state. These are basically different allotropic transformation of the ice. And if you look, there are also points where three phases coexist. So these are also triple point. But conventionally, when you talk about triple point, we basically talk about the point where the liquid, solid, and vapor are in equilibrium. But it doesn't mean this is the only triple point where three phases may equilibrate. This is a special kind of triple point where the liquid, solid, and vapor, these are the three phases equilibrate. Apart from that, there may be triple points where two solid state, one liquid state may equilibrate. Here, for example, if you look into these points, here two solid state and one liquid states are basically equilibrium. Or there is another point you can see there, three solid states are basically in equilibrium. Okay, so triple point may occur depending upon the pressure and temperature. Many different triple points may occur for a pure substance depending upon the pressure and temperature. But when you talk about triple point, standard triple point, it is the triple point where the solid, liquid, and vapor will be in equilibrium. Okay, and this is the only state. Okay, where solid, liquid, and vapor are basically in equilibrium, and this is very specific for a particular substance. For every substance, there is only one triple point. The degree of freedom at the triple point is 0. You do not have any option to specify anything. For example, if you look into this particular phase change diagrams, okay, you can see when the substance is in the state 1, you have to specify both temperature and pressure to specify its state. If you go in the superheated region or in the liquid subcooled region, you need to specify both pressure and temperature or any two independent properties to specify the state. If you go to the two-phase region, that is phase transformation, you have only one independent parameter, but still you have to define two properties. But if you go to the triple point, you have no option to specify any pressure or temperature. It is basically the property of the substance. Okay. So degree of freedom at triple point is 0. Understood this?
Yes, sir.
Now, whatever so far we have seen is basically the PV diagram, TS diagram, okay, so this is entire thing is based on that. Why we are choosing two-dimensional plots? Because we know to specify the state we need two independent properties. We can plot any one of the properties in the x-axis, the other property in the y-axis, and we can have some state points. Okay, and now you think of that there are many properties. For example, if you think of the properties whatever you have studied so far in your thermodynamics and other studies, the properties may be pressure, temperature, specific volume, entropy, enthalpy, internal energy. Okay, all these are properties. So if any two independent properties are known, we can have the other properties. That means any properties can be expressed as a function of two independent properties. So mathematical point of view, you can say that if x and y are basically two independent properties, and if you want to construct a third property out of that, you can say z is a function of x and y. Z could be any other properties. Mathematically, what does this z represent? This represents basically a surface. Z is equal to x and y. Z are function of x and y. So we can write the pressure is a function of temperature and volume or specific volume. So all these thermodynamic states of a substance may be expressed on the surfaces, thermodynamic surfaces, and that give us the different kind of surfaces called PVT surface. Okay. Now, what does this PVT surfaces show? Here we have basically we'll be discussing about the PVT surface for PVT surface. Okay, because we have talked about pressure, volume, and temperature. Other surfaces may be also constructed, but those are not of much interest because as far as properties are concerned, we can measure pressure, volume, and temperature. So accordingly, we can draw these surfaces easily. So this figure basically represents the PVT surface. You can see we have, this is for the material which contracts on freezing. Contraction takes place. And this is the PVT surface for a substance that expands on freezing like water. Okay. So all the points on this surface represent equilibrium state because all the states along the path of the quasi-equilibrium process lies on the PVT surface, since such a process must pass through the equilibrium state. So if you look into the any points here, they basically have passed through some quasi-equilibrium process. In this diagram, the single phase region appears on curved surfaces because in this single phase region, what is meant by single phase region? In single phase region, how many properties are required to specify the state? Please tell me. 2, right? So that's why single phase region should be curved. Whereas wherever there is a phase transformation from solid to liquid or liquid to vapor, out of this P, V, T, P, and T, they are basically dependent. They are no more independent. So they are basically in the two phase regions, a surface perpendicular to the PT plane. They have to be perpendicular to the PT plane because pressure and temperature are not independent to each other. Okay, so these are basically the PT diagram, PVT diagrams for the substances. You can see here these white planes are basically perpendicular to the PT planes. Now, we can directly go from this PVT diagram to our projected diagrams, whatever we have drawn. We may go for the PV diagram, we may go for the PT diagram. Okay, so whatever PV, PT diagram we have so far discussed, that can be directly produced by projecting the PVT diagram on the corresponding planes. Suppose if we project this PVT diagram on the PT plane, what will get the PT diagram, what we have discussed. Similarly, if we project it to the pressure versus temperature diagram, pressure versus volume diagram, it will lead to the PV diagrams. Okay. So similarly, if we plot it, these are basically the figures for the PT diagram and the PV diagram. So if you project it in the PV diagram, it will get the PV diagram for the for the pure substance. Let us say we are considering water. Similar thing will happen for other kind of substances, which basically a substance that expands on freezing. Okay, so okay, understood this? This is for just your information. Okay, the surface plot may be generated because any two properties are basically, they are independent. You may construct other properties, you may obtain other properties. So mathematically, it is basically a surface plot. That surface may be always generated. Or vice versa, from that 3D surfaces, basically 2D surface in a 3D diagram, you can always project it to a 2D plane to get the corresponding variations like PT plot, PP plot. Okay. Any doubt about this point? Anybody? I assume no doubts. Okay, fine. The other important plots which are very frequently used while dealing with steam for power plants, or when you will be studying the refrigeration and air conditioning, will very frequently use this diagram. This is called the HS diagram or the Mollier's diagram. Let me explain the Mollier's diagram first from a mathematical point of view. So HS diagram, what does it mean? The variation of H and S. So if you draw a curve on this HS diagram, what does that curve represents? Okay. So if we want to plot a curve like dy dx, so what is it? What xy plane? At any point, you need to have the derivative dy dx. Similarly, for drawing dh ds curve, okay, you have to get the derivative dh ds at any point, hs plane, okay, corresponding to some other properties which are kept constant. Okay, so dh ds diagram or hs diagram at constant pressure is of primary importance in our applications. So first look into what is H. H is basically enthalpy. Enthalpy is a combined property, which is basically U plus PV. And dH can be written as, if you just make a derivative of this, it will give du plus PdV plus VdP. Now du plus PdV is equal to, what is du plus PdV? Can you tell me? From first law, this is, what is du plus PdV from first law?
dq.
dq. And when we can write dq is equal to TdS?
It's a reversible process.
For the reversible process, okay? For the reversible process, so we are considering the process to be reversible. So we can write dH is equal to TdS plus VdP. Now if you keep pressure is equal to constant, so in that case this VdP term will vanish and we'll get dH ds is equal to T at constant pressure. Okay, that expressions you have got. So what does it mean? The slope at a point on the HS diagram if the process occurs at constant pressure, is basically the temperature at that state. Got this point? If the temperature is high, slope will be high. If the temperature is low, slope will be also low. So that is a mathematical interpretation of DH diagrams. Now look into this particular. So this equation forms the basis for the HS diagram or Mollier diagram. The slope and isobar means pressure is equal to constant, is equal to absolute temperature. So what we can see, now think of the different situations on the HS diagram, starting from point 1, where we have, let us say, we have a solid at minus 10 degrees centigrade, let us say ice. And the pressure corresponding should say, let us say 1 atmospheric pressure. Now if you heat it, what would happen to the slope of that curve? Because you are heating, that heating is sensible heating because it is not a phase transformation. Minus 10 degree ice to 0 degree centigrade ice at 1 atmospheric pressure, during this process, temperature will vary. Because temperature is varying, the slope of this curve ds at constant P will also vary. So if you go from process 1 to 2, state 1 to 2, that means minus 10 degree centigrade ice to 0 degree centigrade ice at 1 atmospheric pressure, the slope of the curve should increase. Understood this point? Okay. Then, what is state 2? State 2 is the 0 degree centigrade water, the solid. Then 2 to 3, the slope has to be constant. Can you tell me? 0 degree centigrade solid to 0 degree centigrade liquid, because temperature will remain constant. So ds on this curve, temperature will remain constant. During the phase transformation process, temperature will remain constant at constant pressure. Then again, we have the saturated liquid corresponding to melting. That saturated liquid will be converted to saturated liquid at 100 degrees centigrade if we keep pressure is equal to 1 atmospheric. So during this process, again sensibility, temperature is increasing. And as temperature is increasing, the slope of the curve should again increase. Then after that, again slope will remain constant, because 100 degree centigrade liquid to 100 degree centigrade vapor, during this process 4 to 5, the temperature will remain constant. So ds at constant P, where T will remain constant. So if you show the phase transformation from liquid state to the vapor state on the HS plane, it will be a constant temperature line. Temperature will be equal to constant. So slope of the curve will be remain constant. And after that, from saturated vapor to the superheated vapor, the curve's temperature will keep on increasing. So if with this basic idea, if one draws the HS diagram, it will get a diagram like this one. Okay. So this is the phase equilibrium diagram for some substance. Let us say this is your triple point line, this is your triple point line, this is the triple point. So if you go 1, 2, 3, 4, 5, 6, what I have drawn, it is basically the same curves. Okay, so 1 to 2, the slope will increase, then 2 to 3, solid to liquid transformation, slope will remain constant, then 3 to 4, again slope will increase, then 4 to 5, slope should remain constant, then 5 to 6, again it will increase. And this is the saturated vapor, this is the critical point line. So this is what is the HS diagram, basic trends. Now, if you look into this HS diagram more with a better insight, if you look into that, during the phase transformation process, what is the speciality of this curve? If you look into that the constant pressure lines are basically diverging. Why constant pressure lines are diverging? Can you tell me in this figure? The constant pressure lines are diverging. Can you see that? Yes or no? So these are basically the constant pressure lines. It is, we have taken only the liquid to vapor transformation. Liquid to vapor and superheated vapor. These are the three regions we have considered for water. Okay. And these lines basically the corresponding to constant pressure lines, which are basically increasing as you go in the upward directions. Now the basic nature of this curve is that the constant pressure lines are diverging. Why they are diverging? Can anybody tell me? Nobody, somebody should speak up. Okay, it's already written. I hope you people don't want to speak out. So let's take it that way. So one thing is that you should interact. Can you listen me first? Tell me. I have to ensure that. Can you listen me?
Yes, sir.
Okay, fine. Okay, so the constant pressure lines are basically diverging in the sense, because if you increase the pressure, the corresponding temperature for phase transformation will increase. And we have seen that ds at constant P is temperature. Since temperature is increasing, the slope of the curve will also increase. So these curves will diverge. And you can see the constant temperature lines are also shown here. And the constant temperature lines basically diverges after the saturated vapor line. Before the saturated vapor line, the constant temperature lines and constant pressure lines merges. They are parallel to each other. Why they are parallel to each other? Because at this point, pressure and temperature are no more independent properties. They are dependent. So they will be parallel. After that, you can see the constant temperature lines are basically diverging from the constant pressure lines, because after that pressure and temperature are no more dependent. Moreover, if you increase the temperature, the constant temperature lines will become more and more horizontal. It will be horizontal means with increase in temperature, H will remain constant. Okay, so it means that because if you increase the temperature, they will basically exhibit the behavior of for an ideal gas. You can see it is a function of temperature only. Okay, so at higher temperature you can see if we increase the temperature, entropy will increase. Okay, so this is the HS diagram. So if you look the more generalized HS diagram, this is how the diagrams are basically represented in thermodynamic tables books. Here you can see the green line shows the steam temperature lines. So you can see there are 50 degrees centigrade temperature, 100 degrees centigrade, 150 degrees centigrade. These are basically lines parallel almost to the H axis. Okay, the blue lines gives the absolute steam pressure. Okay, so these are the pressure lines. So 0.1 bar, 0.2 bar, 0.3 bar, 0.05 bar, these are the 0.01, 0.02, like that way. This is 0.2, 0.51. These are the pressure. Up to 500 bars, this is shown here. Red lines gives the dryness fraction lines. So if you go along the saturated vapor line, the dryness fraction is 1. If you go along the saturated liquid line, the dryness fraction, it is not shown here, it will be dryness fraction will be equal to 0. So all these red lines corresponds to the dryness fraction lines. Okay. So if you look into the actual molecular diagrams, you will see this kind of plots. So if you want to find the, let us say we know what is the special use of this HS diagram. Suppose for the steam, if H and entropy are known, okay, H and temperature are known, or let us say pressure and temperature are known, which are basically more important properties. Suppose pressure and temperature are known. Oh, let us somebody says that my pressure is 0.2 bar and temperature is 150 degree. So what that 0.2 bar line starts with 150 degree centigrade line. Okay, 0.2 bar basically here it is 0.2 bar, and 150 degree centigrade temperature lines is basically this one. Where does it cut? Okay, that will be the state point. Now look into, let us say, 100 degree centigrade temperature. Okay, this is one atmospheric pressure conditions. So this is the situation. That is where they basically cut. Okay, and like that way, if we know the pressure and temperature, we can easily specify what is the state of that substance, whether it is within the two-phase gradient or in the superheated region. Moreover, you will find there are different kind of constant enthalpy processes. Throttling is a constant enthalpy process. Okay, during this process, you can see, let us say if we take some state, let us say steam at 100 degrees centigrade, let us say 250 degrees centigrade temperature, and the quality of the steam is, let us say, 0.95. So this is the point, and the corresponding pressure is, let us say, we want to fit the pressure to be, let us say, what will be the corresponding pressure? 250. This is 0.5. Okay, so corresponding pressure is 0.5 bar. Now if you expand it to a lower pressure, okay, and in an isentropic manner, so you will get along this line, horizontal line. So it will be a constant enthalpy line, and it will come to some point where the steam is basically superheated vapor, or maybe some steam at a lower pressure but at higher qualities if it is in the two-phase region. So those kind of processes, constant enthalpy processes, may be better analyzed with the help of this HS diagram. Okay. So one of the problem with this HS diagram is that because it's a graphical representation, you have to take the data. So manual error during collecting the data will be more, so error will be more, but it will give you very good approximations, first-hand approximations about the state and the change in state and the corresponding property changes. If we look into the HS diagram. HS diagram may be drawn for the different kind of substances. Maybe for the different kind of refrigerants, it is available. For the water, it is available. So what we did in the last class, we have already discussed about, so this is basically the different kind of process diagrams we have discussed. If possible, we will discuss more. For the time being, we will shift our attention to some other topics. So this is the things we have already discussed. We have seen what is the quality of the steam, and we can, if you know the quality of the steam, we can define the properties in the two-phase region based on the property values in the saturated liquid state and the saturated vapor state and the quality of the steam. For example, if some steam is in the two-phase region, that means it is a mixture of saturated liquid and vapor, okay, wet steam. So in that case, if we know the quality of the steam, X, and if we know that either pressure or temperature, we can find the value of HF, we can find the value of HFG, we can find the enthalpy. Similarly, entropy, internal energy, specific volume, all those properties can be obtained. Now, in the steam table, if you look into the steam table, in thermodynamics, we are basically interested about changes in property values. If you go from one state to another state, how much heat transfer will take place? How much entropy change will take place? How much internal energy will take place? That changes are very important. But when we talk about changes, our reference states are basically not very important. Whatever may be the reference state you define, whether it's atmospheric pressure conditions, 25 degrees centigrade temperature or triple point or something, the changes are not going to be affected. Okay, whether your reference point is 0 and then you take the changes, or reference point is 10 and you go for changes at higher values, that doesn't matter. Okay. But when you want to tabulate the data in the steam table, you have to give some values. Let us say, what is the steam property at 80 degrees centigrade where the pressure is 0.2 MPa? What is the properties of the steam when its temperature is 150 degrees centigrade and pressure is 1 atmospheric pressure? Now, when you'll be giving these values, you have to set some reference point. And with that reference point, you have to tabulate the values depending upon the thermodynamic relationship. So in steam table, by convention, it is taken that the saturated water at the triple point. Okay, triple point means the temperature, saturated water at temperature of 0.01 degrees centigrade and pressure is 0.00611 bar. At triple point, the internal energy and entropy of the water is arbitrarily set to 0. There is no basis. The only basis is that we have to set the values at some reference point in order to calculate the property values at some other point, other state point. And it doesn't actually alter the result, because whenever we'll be dealing in thermodynamics, you'll see we are interested about changes. How much heat transfer takes place when water is heated from 0 degrees centigrade to 100 degrees centigrade. So it basically gives the difference between enthalpies between these two states. And when you go for the difference in enthalpies, what is the reference point about which the enthalpies at the two states are evaluated? That is basically cancelled out. But still, for the conventions, that is why for the conventions, the internal energy and entropy basically at the triple point are set to 0. Now, if you put internal energy and entropy to be 0, H cannot be set 0, because in the triple point, the pressure value is non-zero, and specific volume of the fluid cannot be 0 of a given mass. So H value will be very small. So if you look into the steam table, you'll find that in the triple point, internal energy value is 0, entropy value is 0, H value is very small. Okay, some books, if you take only 2 decimal places accurate, so they will write it is 0.00. That means there are, if you go for hard decimal places, you will get some non-zero values. Okay, so this is the basis by which the steam values are basically tabulated in the steam table. And these tables will be very frequently used. We discussed in the last class, this one. Now, one thing is very clear, if you look into these expressions, when we'll be dealing with the properties of the pure substances, we'll be applying this knowledge to our engineering applications or engineering devices. We need to calculate, for example, for power plant applications, the property called the quality of the steam at different states in the two-phase region is very important. Now, how to get that property values or how to get the quality of the steam? We'll be discussing about that, how to get the quality of the steam in this particular topic. Next. Before that, let us have some idea about what is evaporation and what is boiling. Some very basic idea. Okay, then we'll go to that. You can see here that evaporation means that if there is a liquid at certain temperature, that temperature is below the boiling point temperature corresponding to that pressure, there will be an interface between the liquid and some other kind of maybe air. And in that interface, there will be vapor of that particular liquid. Okay, and that vapor is always dry saturated vapor. This term is very important. When there is a liquid, let us consider a pond, okay, or some water body. Just at the interface of the water body, above there will be a layer of the vapor. What is the state of that vapor? It is dry saturated vapor. But that means in that layer, there is no liquid, only vapor of that particular substance is there. Okay. So during evaporation takes place basically below the boiling point temperature. Okay. And the vapor pressure, let us say, depending, so now air has got some, let us consider the evaporation process of the water. So we have some water in a water body. At the surface of the air and the water, there is a thin layer of the vapor. There is a vapor layer, and that vapor basically exerts some pressure on that liquid. And that vapor pressure depends upon the concentration of the vapor in that particular layer. And that concentration of vapor depends upon the total, the moisture content in the air also. Because it is the moisture content in the air that drives that vapor from water body to the atmosphere. That is how evaporation takes place. Okay, and we know so it will exert some vapor pressure, and that vapor is a dry saturated vapor. When I talk about a boiling phenomenon, boiling is basically takes place throughout the media, and during the boiling, the temperature is basically higher than the saturation temperature, or T is greater than the boiling point temperature. And here you can see as the water bubbles are basically forms in vapors, and they goes and collected, they basically entrain some amount of water into vapor choke. So if you consider a container, closed container, and if you boil some water, whatever water which is collected at the top, this is a wet vapor. Its quality is less than 100%. Whereas the vapor which is at the interface of the liquid and the vapor during the evaporation process, that is dry saturated vapor, its quality is 1. This is a very fundamental concept. Okay, So this concept will be required when you'll be dealing with the properties of the water in different situations. Maybe you will apply your concept during psychometric calculations we'll be discussing in this class, which deals with the presence of the water vapor in the air and its consequences. And at the same time, we'll be talking about boiling, which is basically a typical phenomenon which takes place in a boiler to produce superheated steam. So whatever we'll get, it is basically wet vapor in case of this boiling phenomenon. Okay. Now, we want to find the dryness fraction of a given steam. Suppose we are given with a steam with 2 atmospheric pressure. Okay. We know that the steam is a wet steam. It is not a dry saturated steam, it's a wet steam. That means it's a mixture of saturated liquid and vapor at that particular pressure, let us say 2 atmospheric pressure. And somebody asked me what is the quality of that steam that we have to experimentally find. Okay. So how to do that? A device, special device is called throttling calorimeter. Throttling calorimeter is used to experimentally determine the quality of the steam. So what is done here? Here in this process, let us say we have taken a steam from the steam drum. This is the sampling tube. Okay, what steam we are taking? We are taking wet steam, which has got a quality in between 0 to 1. And we know what is the pressure of that steam at section 1. The pressure at which steam is produced and it is sampled. That is the pressure, state 1. Now, this steam is throttled through a throttle valve to a state 1. What are the things changes during the throttling process? Can you tell me? What happened to the pressure during throttling process? Please tell me, anybody? It's a very trivial question. During throttling process, what would happen to the pressure? It will increase, decrease, or remain same?
Large reduction in pressure.
Large reduction in pressure. What would happen to temperature? See, large reduction in pressure is not a good term. During throttling means all of a sudden you change the pressure. Okay. Large is a magnitude term. Suddenly you change the pressure. Now what would happen to temperature? Tell me. Temperature will increase or decrease? Any idea?
Decrease.
Temperature will decrease. Anybody else? Any comment?
So basically enthalpy remains constant.
Enthalpy remain constant, that we know. What would happen to temperature? It will increase, decrease?
Sir,
That depends. Increase. Okay, let us see when it will increase or when it will decrease. So one thing is that enthalpy will remain constant, pressure will drop, and because this is an irreversible process, throttling, what would happen to entropy? Entropy will increase or decrease?
Sir, increase.
Entropy will increase. Okay. And what would happen to the state? State 1 is a wet saturated steam. It will remain wet saturated steam. What would happen to the quality? Quality will increase, decrease, or it will become superheated. Any idea? Oh, let us talk about it. So the basic idea behind determining the quality of steam during using a throttling calorimeter is that the idea is that what are the two important measurable quantities which we can very easily measure, pressure and temperature, right? So in the subcold region and in the superheated region, pressure and temperature are independent. That means if we know pressure and temperature, we can specify the state. But in the two-phase region, that is in the wet mixture of the saturated liquid and vapor, in the two-phase region, pressure and temperature are not independent properties. So if we measure the pressure, temperature is also fixed. We cannot measure the quality. But by somehow, if we can bring that steam from saturated liquid vapor mixture to the superheated region, keeping some properties constant, just like in a throttling process, enthalpy will remain constant. So if we bring that steam from the two-phase region to the superheated region, in the superheated region, then we measure the pressure and temperature, and if we know the measure and pressure and temperature, we can specify the state. And once we specify the state, we can find the value of H. Once we know the value of H, that value H will remain constant during the throttling process. So H2 will be is equal to H1, and we can find the quality of the steam. That is the very basic idea. So you have to bring that steam from the wet saturated state to the superheated region. So throttling should be done in such a fashion that the state 2 is in the superheated state. That point is clear to you? Yes or no? For measuring the quality of the steam. Is that clear? Why that state 2 has to be superheated?
Yes, sir. Yes, sir.
Okay, so that we can measure pressure and temperature, and we can correlate it. So during throttling process, in this particular case, temperature will drop, pressure will also drop, but steam will come from the two-phase region to the superheated region. So have you studied inversion curve? Joule-Thomson coefficient and inversion curve? Yes or no? Just tell me.
No, sir.
Leave it. Okay, no. So if you look into the Joule-Thomson's coefficients values for some range of this, for the same substance, in some range of pressure and temperature, you'll find that the value of Joule-Thomson coefficient is negative. Okay, and in some regions, the value of the Joule-Thomson coefficient is positive. Okay, so depending upon that, inversion curves are generated. Okay, so I will explain that to you in the next class. I do not have this inversion curve with me right moment. I will explain it. So depending upon the value of the Joule-Thomson coefficients, you will see sometimes it becomes 0, sometimes it becomes negative, and sometimes it becomes positive. So depending upon that, during the throttling process, whether temperature will increase or decrease, that is determined. Now come back to our own discussions here. Here we will consider that the temperature will drop, but the state 2 will be the basically the superheated vapor state. So what will be done? Once it will come to the state 2, we will measure its temperature and we will measure its pressure, and we collect the condensate. So how much steam is basically collected, that will give us the total mass. So once we know the pressure and temperature at state 2, it will give you the value of H2. Once we know the value of H2, we can calculate the properties of the steam. So here you can see in this figure, the basic thing is basically shown. The throttling process is shown. The actual figure basically, this is a schematic of the flow diagram of that particular throttling calorimeter and its processes. So let us say we have the steam at state 1. P is equal to P1, and there will be some corresponding temperature, and let us say these are the constant quality lines. X is equal to x1, x2, x3, like that we can draw it. Let us say my quality at this state 1 is x1. My objective is to find what is the value of this quality. Experimentally you have to determine it. For that, what we'll be doing, we will be throttle this thing to state 2, P2, where the pressure is 2, P2 is lower than P1. So if you throttle it, you can see this is connected with a dotted line, not a continuous line. Can you tell me why it is dotted line? Why it should not be a continuous line?
Because it is a irreversible process.
Irreversible process, and all the process on the TS diagram are basically passes through quasi-equilibrium processes. So because it is irreversible, that's why it is dotted. Now if you look into that, as it changes its pressure, temperature is dropping, but it is coming to the superheated region. Now depending upon the changes in pressure in the throttling process, whether the state 2 will lie within the two-phase region, let us say here, or in the superheated region, that will determine. So you have to change your pressure setting such a way, you have to expand to that pressure depending upon the given quality of the steam, that it basically goes to the superheated zone. Then only your pressure and temperature will be independent, and you can measure those things to find the enthalpy at that stage. So once you come to this state basically 2, what you'll get is that we'll get pressure P2, temperature T2. So you get the value of H2 from the steam table. So once you know the value of H2, we know enthalpy throttling is basically constant enthalpy process. It takes place in an adiabatic manner. This is adiabatic but not reversible, irreversible process. This is so H1 is equal to H2. Now what is H1 at state 1? H1 is basically in the two-phase region. So if the quality at state 1 is X1, so quality is known is X1, so H1 will be equal to HF plus X into HFG. So we can write X is equal to H2 minus H of F1 divided by HFG. So using this formula, we can find the quality of the steam, okay, using the throttling calorimeter. Now this is the working principle of the throttling calorimeter, you can see, and the corresponding processes are basically shown in the TS and HS diagram. In HS diagram, you can see the horizontal line is basically the constant enthalpy lines. Let us say my pressure is P1 and the corresponding state is 1. So P1 and P2 are two constant pressure lines which are diverging. So if you throttle it from pressure 1 to pressure 2, depending upon the value of pressure 2, it will lie at some point at H1 is equal to constant. So if my pressure is such that it will end up to the superheated region, so we can find pressure and temperature at that state, and you can use this formula to find the quality of the steam. The same thing may be done by electrical heating also. Here the basic objective is to take that steam from your two-phase region to the superheated region so that pressure and temperature become independent of each other. So what we have some wet steam, and then we basically heat it, maybe electrical heating. And after heating, it becomes superheated. So let us say we have the state 1, and then we are heating it to some temperature T2, and so that its pressure will also change during the heating process, and we can measure both pressure and temperature. Now, what equations we can apply here? If we apply the steady flow energy equations, the enthalpy of the steam which is entering, if you consider per unit mass, for unit mass, the enthalpy of the steam which is entering plus the heat transfer per unit mass should be equal to the enthalpy of the steam which is leaving. Now, the enthalpy of the steam which is leaving can be evaluated based on the data of pressure and temperature. So H2 is known. So H2 minus H1 is basically the rate of heat transfer per unit mass of the fluid flow. So using that electrical heating technique, we can also find the quality of the steam of unknown quality of a steam, the value of the quality of the steam which is not known to us. Okay, so in the HS diagram, it will look like this. Here you can see H is no more constant. It is being heated up, so enthalpy will increase because we are heating it. Now the problem is that with this process, that for measuring the quality of the steam, definite degree of superheating is required. Suppose if we are considering a steam at 1 atmospheric pressure, what is superheating? Superheating means the difference between the saturation temperature and the temperature which is prevailing. That difference in temperature is called the degree of superheating. For example, if you consider 1 atmospheric pressure, in 1 atmospheric pressure, saturation temperature is 100 degrees centigrade. And if the steam is at 110 degrees centigrade, the degree of superheating is 10 degrees centigrade. Now, to measure the quality of the steam properly, minimum degree of superheating is required. That means if your pressure is 1 atmospheric, let us say a minimum degree of superheating required is 5 degree, then
sir.
the proper, yeah.
Sir, time.
Yeah, sorry. Okay, fine. So we'll start with this point in the next class.
Okay, sir.
Also, sir, will you be sending this PDF, because the last few PDFs haven't been sent till now?
Okay, actually what I was thinking, I actually update this PDF until and unless, okay, I'll share it now, and at the end of this lecture, when it is completed, then again I'll share the same PDF because PPT because I keep on changing it as the topics comes. Okay, so
Okay,
for
sir.
the timing you can use it, and the last one you use for the final one. Got it?
Okay, sir.
Thank you.
Thank you, sir.
Okay, you can leave.